Okay, so today we are learning about trigonometry, and this is lesson T.1, Introduction to Trigonometry. All right, so our essential question today, how do you use trigonometry to find missing lengths of triangles? So I'll take a moment and respond to that. Okay. All right, so in order to do this assignment, you're going to need a calculator. So let's all click the link for the desmos.com scientific calculator. If you have your own calculator that you want to use, as long as it is scientific, so it can't just be like one of those basic little calculators that has to have more details on it, then that's fine. A graphing calculator will also work. But this is a really great online calculator that will be helpful to us. So everybody needs to click that now. Okay, click that calculator link. All right, I'm hoping everyone got it. I'm going to change my slide in 3, 2, 1. You'll want to have that calculator on like a different tab where you can just switch back to it every once in a while. Okay. All right, so we're going to start here by reviewing our methods for finding missing sides of triangles. And we already know a couple different ways to do this. So notice in these triangles, we're being asked to find the missing side using the Pythagorean theorem. And notice that both of these triangles are right triangles. That means they have a right angle. They have to be a right triangle to work with Pythagorean theorem. And we also would need to know at least two of the sides of the triangle in order to find the third side using this theorem. So to remind ourselves, Pythagorean theorem is a squared plus b squared equals c squared. And then we need to label our sides. So in a right triangle, the side opposite the right angle is always our C, which is our hypotenuse. And our two legs, the shorter sides, this 5 length and 12 length, can be our A and B, and it doesn't matter which one's which. And then we substitute in our values and solve for the one we want to find. So in this case, here's what we get. All right, so I'm just going to keep going with this. If you want to do this on a separate sheet of paper because it's just hard to write with your mouse or whatever, that's totally fine. If you feel like you understand this and you've done this a bunch of times, you remember it, and you don't know if you really need to, you don't know if you really need to like go through a couple of these problems again, that is your judgment call. This is not the learning goal for today. This is just a review. So now to find our C value, I square root both sides, and that gives me that C is equal to 13. So there's our missing length is 13. The second problem is we'd use the same process, just be careful of your sides because here we have our legs A, B, and then our hypotenuse C. Now we're trying to find A rather than C. So when you set up your Pythagorean theorem, you're plugging in numbers in different places. So like in this one, we don't know A. B is 3, so 3 squared equal to root 10 squared. And again, I'm just going to work through this problem and try to solve for A. So I have A squared equals 3 squared. Oops, just kidding, not equals. Plus 3 squared, which is 9, equals. When we take the square root of 10 and then square it, we actually just get 10 back out. The square root and the square undo each other. Um, so now get a by itself, subtract 9, and it looks like we get a squared equals 1. And 1 times 1 is 1, so a is 1. So there's our missing side, it's a 1. All right, so that's one method. So Pythagorean theorem is totally great. It works always for a right triangle with 2 known sides. That can be something you can always use when you already know 2 of the sides of the triangle. All right, I'm going to go ahead and go to the next slide. So if you need to screenshot or whatever, that's fine now. I'm going to clear in 3, 2, 1. Okay. All right, this is a different way of finding a missing side of a triangle. So now what we have is this situation where we're trying to find the height of this building. And notice how in this triangle, you don't have to circle it, just listen for a second. Notice how in this triangle, we know the base of the triangle, which is like the length of the building shadow. And we're trying to find the height of the triangle, which is the height of the building. But that means we only know one side on the triangle. We know one side, not 2 sides. So we can't use Pythagorean theorem for this. It is a right triangle though, because buildings stand up and down. So we have a right triangle, but we only know one side and we're trying to find the other side. And as far as we know, when that happens, what we need is similar triangles. Because if we have a triangle we know is similar, like this one over here, then we can set up a proportion between the 2 triangles to solve for our unknown side. It's like, we can't use Pythagorean theorem, well, hopefully there's a similar triangle nearby that we can work with. So let's talk about the way we set up our proportion. And this, I'm actually setting this up in a strategic way that will connect with what we do next. So notice how we have the height of the building and we have the height of this little stick over here. They both have a shadow. So our shadows correspond, our heights correspond. Also, what's true is the ratio of the height to the shadow will be the same on both triangles. Because remember, similar triangles have proportional sides. So the way the sides relate, 3:5, will be in the same ratio as how these sides relate. If you're thinking about scale factor as a way to find h, that's totally fine. You can see that the 3 was multiplied by 4 to get 12, so h would have to be 5 or just 20. So we're looking for an answer of 20. But if you didn't see that right off, we can also solve this using cross multiplication. So I'm going to do that. I have 3 times h, and then I multiply this way, equal to 5 times 12, which is 6p. And then I need to solve for h. So I just divide out my 3, and it looks like h is equal to 20. And because this problem has, like, I don't know, a context, it's a building, I'm going to include my units on my answer. All right, so recap. We know how to find a missing side of a triangle when we know of a right triangle, when we know 2 of the sides already. And if we only know one side of the triangle, we can use similar triangles to find the missing side. But what if we didn't have that special similar triangle helping us out? What would we do then? All right, so here we go. So this is where we, have a conflict. Since we know how to find side lengths of right triangles using Pythagorean theorem and similar triangles, but what happens when we only know one side length and an angle of a right triangle, but we don't have a second triangle to compare it to? So now we have a situation where we don't have enough information to use similar triangles or to use Pythagorean theorem to find the length of B. So we need another way. And that's where trigonometry comes in. So I'm going to show you this short video that gives you a little introduction to trigonometry, and then we will go through many problems and hopefully clarify any points of confusion that come up in this. I would like you to pay close attention as I show this video.
You may have heard the term trigonometry before. It sounds really big and fancy, but it's really just a word for math about triangles. I told you before that mathematicians really like triangles. When we had an unknown side of a triangle that we wanted to find, we looked at a similar triangle. One of the interesting things about similar triangles is that because they are scale models of each other, the ratio of one side to another is the same across similar triangles. Okay, so what does that mean? Well, consider these similar triangles. Say, triangle ABC is the original triangle, and we've scaled it by a factor of 2 to get triangle DEF. Let's look at the ratio of side AB to side AC, which is the hypotenuse. Written as a fraction, it's 3/5. If we do the same for the corresponding sides in triangle DEF, the ratio of DE to DF, we get 6/10, which can be reduced to 3/5. The ratio is the same. This is true for any triangle similar to triangle ABC, because the sides of similar triangles have all been scaled by the same amount. We could say that DE is really just 2, the scale factor, times AB. DF is 2 times AC. So DE over DF equals 2 times AB over 2 times AC, and we can divide the top and bottom by 2 to get AB over AC. This would work the same way if the scale factor was 3 or 5 or 0.25 or anything. Now, consider angle A. Because similar triangles have the same angles, all triangles similar to triangle ABC will have that angle. And if we took the ratio of the side opposite A to the hypotenuse, we would get the same ratio for any triangle that is similar to triangle ABC. Well, that ratio of the opposite side to the hypotenuse is important enough that we gave it a name, the sine of an angle. You may have seen the sin button on your calculator before. We only need an angle to calculate the sine because the ratio of the opposite side to the hypotenuse is the same for all right triangles with that angle. There are other ratios like this as well. Cosine, or cos, is the ratio of the adjacent side to the hypotenuse, and tangent, or tan, is the ratio of the opposite side to the adjacent side. This is a little bit abstract, so don't worry if you feel confused. The important thing to understand is that trigonometry is based on the properties of similar right triangles, and that by understanding similar triangles, you can better understand what sine, cosine, and tangent really mean in the future.
Okay. So I know there's probably things there that you got from that and other things that maybe didn't quite connect, and that's okay. We're going to go through this whole idea on our slides, okay? In this, first things first, before we can use trigonometry, before we can use sine, cosine, or tangent, what we need to do is some setup with our triangle. So we need to, one, understand what needs to be true about our triangle before we can actually do trigonometry. So first things first, we need to make sure it's a right triangle. And I see this right angle symbol here, so that tells me I have a right triangle. So I'm good to go. So I'm going to make a note to myself that we need a right triangle. Okay, so this is a right triangle. The other thing we need to be aware of is the angle that we sort of focus our attention on. So the right angle is essential for us to do the problem in the first place, but then we kind of ignore it and we look for one of our other two angles, an acute angle. And angle A here is the one that is chosen in this particular situation. And I can tell that because of this little symbol right here. So this little symbol has a special name. It is called theta. And theta is a Greek letter that represents the measure of an angle. So it's really not meant to be like a confusing thing. It's like a variable. And we're actually going to call this angle the reference angle. And because this is what we kind of base our work on. So we have theta. It tells us which angle to focus on. Sometimes our theta will be given to us, like with a degree measure, and sometimes it won't. So sometimes we're trying to find theta, and sometimes we're trying to find a side length using theta. So there's that. The next thing we need to be able to do is recognize how the sides relate to theta. So we label each side as the opposite of theta, the adjacent to theta, or the hypotenuse of the triangle. So hopefully we all understand that the hypotenuse of the triangle is opposite the right angle. And that's always going to be true. So the hypotenuse doesn't change in a right triangle. It's always the side opposite the right angle. It's always the longest side. But depending on which angle we choose as theta, like in this case, it's angle A, but theta could also be angle C, that can determine what our opposite side and our adjacent side are. So opposite is the side that does not help to form theta. The hypotenuse is one side of theta. This edge is the other side of theta. This side with B on it, this side does not form theta. It's opposite. And that leaves this side over here, down here as the adjacent. And adjacent is just another word for next to. So the adjacent side is next to our angle theta. So labeling opposite, adjacent, and hypotenuse is essential to doing a trigonometry problem. All right, oops. Okay, I'm having a little allergies. So sorry. Okay, now here's where we get back to those trigonometric ratios. The trigonometric ratios tell us which sides of the triangle to put in ratio with each other. So you can see how the triangle is all labeled already for us. We know where the theta is, we know where opposite, adjacent, and hypotenuse are. And now we have sine, cosine, and tangent telling us what sides we should put in a fraction. And when we say opposite over hypotenuse, we mean like if we have a length for the opposite, we put that number there in that fraction. If we have a length for the hypotenuse, we put that number there in the fraction. So in this case, the sine is opposite over hypotenuse. The cosine of the angle is adjacent over hypotenuse, and the tangent is the opposite over adjacent. Not a lot to try to remember. So we have this special mnemonic device called SOHCAHTOA, which helps us to remember which side ratio goes with which trig function. So down at the bottom, you can see how we have sine is opposite over hypotenuse. And cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So, ka, toa. And this is this thing that's going to help you remember which ones go with which one. So this is sort of a reference slide here for us. But I put SOHCAHTOA on every single slide going forward so that we can refer to that mnemonic device as we go. So this slide now is our opportunity to practice setting up a proportion or an equation using sines, cosines, and tangents of a triangle. But before we can do that, we need to label our sides of this triangle. Excuse me. So notice we have theta down here on the bottom left. This side that's 5 units long is going to be our hypotenuse. So I'm shortening it to HYP just for, to make it less to write. The side opposite angle theta is 4 units long. So here's our opposite side. And the side adjacent is down here. This is adjacent. Now that I've had those sides labeled, I have everything I need to fill in my equation. So I'm going to start with blue, and we'll do the sine. So in the sine equation, this is really important, the structure of this. All right, we start with S-I-N, that's short for sine. Then we put theta, and you do need to write theta. Sine of the angle, sine theta, is equal to opposite over hypotenuse. And that's all we're practicing doing here. So now I'm going to change my color and let's do the cosine. So cosine, cosine of theta is equal to adjacent over hypotenuse. So 3 over 5. And tangent of theta, or tan theta, is equal to opposite over adjacent. So in this particular scenario, we know all the side lengths already. What we don't know is the angle. And we actually don't have a tool to solve this yet. We will learn that in a couple, not today, but in a later lesson. But we did need to practice this idea of setting up the equation. All right, now what's nice about this is what this does is it gives us a tool to be able to find a missing side. And what we want to remember is that every single triangle, this is the same triangle that she was showing us in the video, every single triangle that has sides 3, 4, and 5, or some multiple of that, like a dilation, like a sides 6, 8, and 10, the ratios we would get for the sides compared to each other would be the same once we reduce them every single time. So essentially what we're doing is we're creating a tool for ourselves that gives us like information from a similar triangle without actually having the physical similar triangle there for us. And that enables us to solve problems of missing sides with less information. All right. So now let's do one. Let's solve that triangle that we were looking at from a previous slide. So see in this triangle, we know the angle, we know one of the sides, but we don't know B. So we don't have enough information in this triangle to use Pythagorean theorem. We don't have a second triangle that's similar to be able to compare it to. We have to fall back on this idea of trigonometry to find the length of B. So what I have here is a set of steps to go through. So step 1 says to label the sides opposite, adjacent, and hypotenuse. So first off, just to be clear, 36 degrees is our theta. That's our theta angle. So we do our opposite and our adjacent in relation to that angle. So 18 right here, that is definitely our hypotenuse. It's always opposite the right angle. This side down here is adjacent because it's right next to the theta angle, 36. And that leaves this one over here to be the opposite. And once we have those labeled, this gives us some clues about which trig ratio to use. So step 2, which trig ratio should we use? Now we have to think about what information we have and what information we want. We know that 18 is the hypotenuse. So that means we want to use it. We have the hypotenuse. We're going to use one of these trig ratios that has an h in it, that has the hypotenuse. And what we're trying to find is the length of b over here, the opposite. So we want the trig ratio that relates the opposite and the hypotenuse. The adjacent side in this situation has nothing that's helpful. We don't care about how long it is. It doesn't give us a length already, so we leave it out. So we're looking for the purport or the ratio that uses opposite and hypotenuse, and that would be right here. See, opposite over hypotenuse is sine. So we labeled our sides, we determined our ratio. Now we need to set up our proportion. Okay, so here's what we do exactly like last time, but this time we have a 36-degree angle we can plug in. So we have the sine of 36 equals opposite, which is our unknown b, over hypotenuse, which is 18. All right, now the next part is to solve. So we have now set up our proportion. Our next part is to solve. And in order to do that, we're going to have to use our calculator. So what I'd like you to do is open up your calculator. My calculator up for you. Okay, I know my writing's all over it, but there's the calculator. Can you see my calculator? Hopefully you can see it. Okay, so we are going to use the sine button, sine, and then 36. So if you click sine and then 36 and enter, you can see how we get 0.58778, blah, blah, blah. And what we want to do is round that to 4 decimal places. So it's 0.5878. So back to this. Let's pick a new color. I'm going to rewrite this as 0.5878, which is equal to b over 18. So all I did was calculate this number, sine 36 in the calculator. If your calculator is giving you a different number, if you have a personal calculator and it's giving you some weird negative number or something, you need to change the mode so that it's in degree mode versus radians. The screen might have deg versus rad, and the mode needs to switch. Let me know if you need help with that. Otherwise, the Desmos online calculator is in the right mode. Okay, now at this point, once I have the decimal, I usually always do this and put it over 1. And the reason I do that is because now I have a fraction equal to a fraction. And once I have a fraction equal to a fraction, that makes finishing my calculation really straightforward for every single situation that could arise. So I'm going to cross multiply, just like with similar triangles. B times 1. B times 1 is B. And then I'm going to do 0.5878 times 18 to get my answer. Sorry, give me a second. Boy, that's not what I wanted. 0.5878 times 18 is 10.5804. All right, so here's how I want you to round these things off. When you're using trig numbers inside your problem, like you punch in sine 36 or cosine something or tangent something, I want your number that you work with to be at least four places after the decimal, at least to the 10,000ths, okay? But then your final answer, you can round to the hundredths. All right. Okay, so I'm going to go ahead and clear, and we're going to do this again. All right, so for this next problem, let's start again. This time our angle has changed. It's now 23 degrees instead. But we're going to go through the same exact process. So let's start by labeling our sides. So we have hypotenuse, opposite, adjacent. They're not throwing us any curveballs here. So this is a really straightforward question. It's very similar to the last one. All right, so step one, done. Now step two, which trig function? So notice, again, we have the hypotenuse is 15. We have the opposite, or we want the opposite, which is A. So that means we're not going to use adjacent. So we're going to use sine again, opposite over hypotenuse. And that's how we set it up. So sine 23 degrees is equal to opposite over hypotenuse. Same process. So again, you punch in sine of 23 which is 0.3907. All right, once you have that, I'm going to go ahead and put this over 1 so that I have like a nice clear proportion set up. And then I'm going to multiply, cross multiply. So A times 1 is A. And this decimal times 15 is, so we have 0.3907 times 15, 5.86. All right. How's everyone doing? So if you have a question, you want to put it in the chat, please do that. I'm happy to answer any questions that come in. Okay, if you need clarity on how did I choose that? What did I do? How did I set that up? All right, I'm going to go ahead and clear. Let's try that again. Okay. Again, same process, every single time, like this is the process. Okay, so we start by labeling. So label our sides. Remember, now this time we have a 37-degree angle. I like to start with the hypotenuse, since I always know it's the same. Next to the angle, this B side is adjacent because that's next to, which leaves this one over here opposite. All right. Now notice how this time the opposite doesn't seem to have anything useful for us. we want to compare the adjacent, which is what we're trying to find, to the hypotenuse, which is what we already know. So adjacent hypotenuse, that's AH. That tells us to use cosine. So it's a slightly different start, but the process is very much the same. So now I'm going to write my proportion. Cosine of theta, which is 37, is equal to adjacent, that's B, over hypotenuse, 8. And now this time when you punch it in your calculator, just make sure you don't use the sine button anymore. You use the cosine button this time, but otherwise it's the same process. So cosine 37, oops. Cosine 37 is 0.7986. And that's still equal to B over 8. And then I'm going to go ahead and put that decimal over 1 so I have a nice fraction compared to my other fraction. And cross multiply. So B times 1, that's B. And 8 times 0.798. Point 7986, excuse me, times 8 is 6.3888. So I'm going to round that to 6.39. All right. So hopefully it's starting to get a little, getting kind of feeling smoother. All right, I'm going to clear my drawing. Okay. All right, so this one's trying to like confuse us by reorienting the triangle, but it's still a right triangle, so we shouldn't have trouble with it really. We just still need to go through the same steps. So we've got 62 degrees is our theta. Remember the side opposite the right angle, that's up here, that's always the hypotenuse. And then it looks like the hypotenuse and this side with x form the angle. So this would be our adjacent. And that leaves this 5 over here to be our opposite. All right, so now first step done. Now we have to determine which trig ratio to use. So this time we're not going to use the hypotenuse. The hypotenuse has nothing for us. We're going to use opposite compared to adjacent. So which one has O and A? And that would be tangent this time. So now I set up my ratio, my proportion. The tangent or tan of 62 is equal to opposite over adjacent, 5 over x. And now we punch it in our calculator, just like before, but this time with the tan button. All right, so I got 1.8807 equals 5 over x. Put it over 1. And now here, I do want to point this out. This time is a little different because the variable that we're trying to find is in the denominator, so that the way that the numbers are going to like work out in our, when we do our cross multiplying, it's going to be slightly different than before because of that denominator situation. So just be very, very careful with your work. But notice this. Look, we have 1.8807 times x. And then that's equal to 5 times 1, which is 5. And we're trying to solve for x. So in order to get x by itself, we need to divide both sides by 1.8807. That will get us our x alone. Five divided by 1.8807. All right, and it looks like 2.66 about. Okay. All right. Hopefully everyone's doing okay. Those of you using the slides, it's looking pretty good. Okay. All right. I'm going to go ahead and clear my slide. Okay, so now what we have is a slide that's really just practice for you. And then the next slide after is closure. So what I would like you to do is use this last, let's use about the next 10 minutes or so to work on these practice problems. And we can check our answers in a little bit. If you are working on a separate sheet, go ahead and just make sure you put your answer up on your slide so that that gives me an idea of how everyone's doing, okay? All right. Let me know if you have questions.